Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is lecture number 59. Now, in the last lecture, we just started discussing about molecular vibrations and vibrational spectroscopy in the context of astrochemistry and detecting molecules in space. I had ended the last lecture by informing you that closer to the equilibrium distance, right, the reduced potential energy surface of any system could be approximated by a parabola, right? Because it is, you can look at the shape, right? It can be approximated by a parabola, and consequently, right? And consequently, the potential energy, you know, because we're just talking about motion along one dimension here, right? So for this diatomic molecule, the potential energy V of x can be defined as half times kx square, which is a parabolic potential, right? Where my x is some arbitrary distance, right? Displacement from the equilibrium position. I'm just going to call it, you know, it doesn't matter whether I define it as r minus re, or I'll use the right symbol, r minus re. Okay, right? Because it's x square, it doesn't matter whether it's re minus r or r minus re. The square is always going to be positive, okay, right? So with this potential form, right, I can use it in the Schrodinger equation, use it in the time-independent Schrodinger equation for this particular potential energy surface, especially closer to the equilibrium bond length, right, to get something like minus h bar square by 2 mu d square psi of x by dx square plus this is the kinetic energy term. You know, I mean, I'm sure you folks are familiar with what I'm talking about, right? Because we've been seeing this to get the energy levels. We solve the time independent Schrodinger equation, right? Because our Hamiltonian is independent of time. That's a very reasonable assumption we can make in these cases. You know, probably go back to some lectures 30, somewhere in the mid 30s or 40s, okay, where I introduced this idea, right? Okay, so this is the kinetic energy term, and then there is the potential energy term, which is going to be half kx square is equal to the energy for this particular system, right? The energy for the system times psi of x, right? Now, just the fact that, you know, I have this extra term here, right? I'm not going to solve this equation. I'm just telling you how to set up the Schrodinger equation, the time-independent Schrodinger equation to model molecular vibrations, right? It is basically that closer to the equilibrium, we can assume a potential form of this parabolic form. V of x is equal to half kx square, right? And it's also analogous in your classical mechanics case with the simple harmonic motion, right? Any two masses, right, bound by a spring which is vibrating to and fro, right? This is the potential energy corresponding to this restoring force. F equals minus f of x is equal to minus kx, right? Where x is again r minus re, and your k is the force constant, correct? Right? I'll be more mathematically precise. You define x to be the modulus of this, okay, right? So here, your k is the force constant and the negative sign in this equation. And the negative sign in this equation comes to indicate that the direction of the force is going to be opposite to the direction of displacement, right? And so, because it's a conservative force, your F is negative dV by dr. From this you get this, and from this you get this, okay, right? This is, high school or introductory college level physics, okay? So we get this sum of the potential, right, to describe the system. Now, once we solve this equation, okay, right? This is the Schrodinger equation for the diatomic molecule whose vibration we are going to be describing. Okay, right? Now, this can be solved. Of course, solving it is a very tedious process, and that involves a specialized quantum chemistry course. I'll be continuing from here. Okay, I'll just call it equation 1. Okay, right? Just take a look at this equation because I'll be going to the other side of the board. This is minus h bar squared by 2 mu, where mu is the reduced mass of the system. Okay, right? And this is the kinetic energy term, and this is the potential energy term, right? And once we solve this, we shall be getting, of course, after applying the boundary condition. Okay, right? Solving it, which we skip here. Okay, skip in this class. And by applying a boundary condition, okay, right? By applying a boundary condition. Now, what is the boundary condition that we apply? I'll come to that. Okay, we get the expression as E is equal to something like mu plus 1/2 h bar omega, where omega is the square root of k over mu, where k is the force constant, and which is given over here, right? F of x equal to minus kx, right? And mu is just going to be the reduced mass, and mu is a quantum number called as the vibrational quantum number, which has values of 0, 1, 2, 3, etc., etc. Okay, right? So this is the energy expression that we get. All right. Now, the most important point to note here is I did not tell you what boundary condition it is. Okay. Now, unlike the case of the rigid rotor, where I could easily, give you a physical boundary condition, that is, after every cycle of rotation, the object returns to the same point, right? That is how you define rotational motion, right? After you make a complete circle, you have to come back to the same point, right? Now, here, it's not so easy to make a physical boundary condition. The boundary condition is actually a complicated mathematical one, wherein, you have to, what is called as truncate a particular series, okay? A vague physical analogy can be made to that mathematical condition. It is that, so the specific boundary condition applied here, I'm just going to call this as BC, right? So the boundary condition applied here vaguely translates into ignoring higher modes of vibration. Right? It's only a vague physical analogy because, more strictly speaking, the boundary condition can be well defined only in terms of math, which we are completely ignoring for our purpose. Okay, right? Ignoring higher modes of vibration. Okay, right? And noticing that this is a vague physical. It's just a vague physical idea about the boundary condition. What I'm not doing is giving you clear-cut mapping between the mathematical boundary condition used and the physical condition, because it's not possible. Okay, right? It's just a vague idea that I'm ignoring higher modes of vibration. All right. So we get this expression. The expression we get is what? E equals nu plus half times h bar omega, where nu can be 0 also. Okay, please note this. Now, we get into this very interesting scenario when my nu happens to be 0. Okay, I'm going to call this expression, I'm just going to call this expression E. Okay, and I will delete this part. I need to, explain some aspects of this curve, so I'll just keep it intact. So this is going to be page number 4 in expression E over here, right? When my nu equals 0, okay, right? In other words, I'm talking about the ground state of the system. Notice that this nu is a vibrational quantum number. This is not, the nu symbol that we use for E equals h nu, right? The frequency. It's just an unfortunate, use of notation. But because several popular textbooks use the same notation, nu, right, to refer to this vibrational quantum number, I'm using it. But if at all I talk about nu as in frequency, I'll clearly mention it to you. So do not be confused. Okay. So when nu equals 0 in expression E, right, my energy is going to be h bar omega by 2. Now, please note this, okay? I want you to, do a comparison, right? Between this expression, when u equals 0, in expression E, versus the energy, okay, right? The energy of rotation based on the rigid rotor model, right, was Bj times j plus 1, right? And what was the condition on j? The lowest value that j could have 0, 1, 2, 3, etc. And the least value of j is going to be 0, right? So the smallest value of E rotation, right, I'll just call it E rot min, is 0. But in the case of vibration, right, in the case of molecular vibration, I'm just going to call it as E vib min is h bar omega by 2, right? And this is non-zero. Please be very clear. It is non-zero because, well, h bar and 2 are of course not zero, and omega is also not zero, because that will violate our problem itself, right? We're assuming that, it is vibrating, right? So my omega is also non-zero, right? And my E vibrational minimum is called as h bar omega by 2. Whereas, in contrast, for the rotational motion, the minimum energy could be 0. Please note this important distinction, okay, right? Now, this E vibe min, which is given by h bar omega by 2, is also what is called as, can you guess? It is very commonly used in physics and chemistry. It is called as the 0 point energy. 0 point energy, or the ZPE in short, okay, right? ZPE, okay? So this is what is called as the 0 point energy, and it would be an understatement to say that this has tremendous implications, not just in astrochemistry, but also in the much broader field of cosmology. Okay, we shall very briefly touch upon the impact of ZPE, okay, or the 0 point energy. All right. So now, if you recall, let's say, whenever, probably somewhere between lectures 20 and 30, I was talking about the potential energy, the reduced version of the potential energy surfaces, right? Such as some figure like this, some curve like this. And I would often tell you, when talking about the vibrational state, I would tell you that if, let's say, this is the ground vibrational state. Look at this line here, this small line over here, right? I'm going to call this as nu naught. And this line here, let's say, is like nu 1. This corresponds to the ground vibrational state, and this corresponds to the first vibrational energy state. Okay. Now, I always do this above the minimum. Let's call this point, okay, right? Let's coin this point as like the bottom of the well. Bottom of the well, of bow, okay, right? This is the bottom of the well. But, I mean, assuming that this is the well, okay, right? So, the lowest vibrational energy was never shown along the bottom of the well. It was always shown slightly above, right? I told you that maybe while discussing in the future class, I'll be explaining why it is. It is because of the fact that your E vibrational minimum, right, is always non-zero. This particular thing, your ZPE, right, is non-zero. Please note this point. So therefore, right, the vibrational state does not correspond to the bottom of the well, but is slightly raised above. Okay, I will explain this even better. I'll again retain this curve. So my ZPE is given by h bar omega by 2 and is not equal to 0. Okay, right? So this is not equal to 0, and what this tells us is that even at 0 Kelvin, in fact, when we're over at very low temperatures, right, we're not going to reach the zero of the energy itself. Okay, this is somewhat analogous to what we see in thermodynamics, right? That the entropy, it's analogous only. Okay, right? The entropy of any system, even at absolute zero, is non-zero, right? So you can kind of think about the 0 point energy as the quantum mechanical version of that thermodynamic statement. Okay, right? I think that's called the third law of thermodynamics, right? So the quantum mechanical version of this, that macroscopic picture, is what we get in quantum mechanics. Now ZP is extremely profound, obviously, because of the omega thing here, right? And what is the formula for omega? We all know that, right? Your angular velocity is like 2 pi nu. Here nu is like, and it's called nu dash, where nu dash is the frequency, right? And therefore this is going to be given by 2 pi over 2 pi root of k by nu, where k is the first constant, right? So your formula for omega is root over k by mu, right? Now I'll write it better. Square root of k by mu, where mu is the reduced mass and k is the first constant. Okay, so now because there is a mu dependence for different isotopes, the ZP is going to be different, right? Clearly. So therefore, from the vibrational spectroscopy, you also get to know about the abundances of the various isotopes, just like we saw with rotational spectroscopy, right? Wherein for carbon monoxide, we looked at the isotopic patterns. Similarly, the 0-point energy, the magnitude of 0-point energies are going to be different for different isotopes in astrochemistry. I mean, let's say, for example, you talk about like H2 versus like D2, right? So the magnitude of ZP is going to be different for different isotopes. Implies, right? Magnitude of ZP different for different isotopes, and this will help us in assigning the features of any vibrational spectrum, both on Earth and from any sample obtained from space, right? To get a specific isotope pattern. Okay, right? We can use this idea that if like there's going to be a magnitude of difference between the two omega values, the spectral lines are going to be reflecting that. So this is a very useful idea in identifying molecules in space. I've written, and this is a useful idea for identifying molecules in space, right? And on Earth. So what I've written is, it's useful for identifying molecules in space and on Earth. Because it's at the bottom portion, I make sure that you precisely understand what I've written here. Okay, right? So the ZP is something that is going to be seen in the spectra, the vibrational spectra of molecules. Okay, now this is its implication for spectroscopy on Earth and also for astrochemistry. But beyond it, it has tremendous implications in the whole field of cosmology itself. Okay, I will highlight that here. So your ZP, right, has fundamental significance in cosmology itself. Now, what is cosmology? If you recall, probably in lecture 2 or 3 of this course, I was saying that cosmology talks about the origin of the universe itself. Beyond just how molecules are formed and how they dissociate, it talks about the complete origin of the universe itself. Okay, right? Now, how is ZP fundamentally important in cosmology? Now, what is this? We saw that, right? We saw that the Schrodinger equation could be written for this system, right? This H2 diatomic. But what is it? It is nothing but an oscillator, right? It is something, some system. If you ignore, the labels H and H, the two atoms, we're talking about two entities, two quantum mechanical entities, a hydrogen atom each, right? In this case, right? Two quantum mechanical entities connected by some spring, right? Which is oscillating, right? Now, the entire universe, okay, right? The entire universe could be thought of, the universe could be thought of as, containing infinitely many coupled oscillators. Okay, right? So the universe, can be thought of as containing, I'll put it this way, containing infinitely many coupled oscillators, which constitute what is called as the electromagnetic radiation. Right? So because we keep talking about an electromagnetic radiation, which permeates all around us, correct? And but the electromagnetic radiation, what could it be defined as? It could, in its simplest version, it could be defined as nothing but, many coupled oscillators, right? Such as, for example, this small oscillator here, right? If you like see that at each point in space there is an oscillation, and you just add it up all over the space present in the universe. Okay, right? You have infinitely many such oscillators, right? And so the ZP for such a system, right, could be written as the sum over, right? So ZP for the electromagnetic radiation, which is one specific definition of one specific understanding of electromagnetic radiation, right, could be nothing but the sigma over, like all modes, right? Your h bar omega by 2, right? So let's say that I'll just put it, some I. If, like, let's say, well, I is the index used for these modes, okay, right? So, and let's say there are infinitely many such things, okay, right? So I sum over all the modes, and each of these modes has a small angular velocity omega, right? Now, by coupling all of this, I will be getting the ZP for the entire electromagnetic radiation present in the whole of universe, okay, right? Now, so the 0-point energy is therefore fundamentally connected with the origin of the universe and the fundamental description of the electromagnetic radiation itself. It doesn't stop here. There is in fact a huge problem, okay, in cosmology concerning the ZP. It is that I'll again need this curve, so I'll go back here. So now the problem in cosmology, okay, due to ZP, I'm just describing the problem in a nutshell, is that, see, if, the 0-point energy of all these oscillators is going to be the sum of all the 0-point energies, right? Say something like sigma over I equals 1 to infinity, h bar omega I by 2, right? Then the 0-point energy of the universe is estimated to be, of the order of 10 to the power 43 hertz. I mean, when expressed in terms of per seconds, right? Recall from our discussion on the rotational constant B, we can always express energy in terms of an energy unit or some kind of wavelength, wave number, or also frequency unit, right? So in terms of frequency, it is this high, okay, right? Now this is just absurd, right? So this is what you would expect based on an understanding of electromagnetic radiation as a system of coupled oscillators. This is the known theory. However, obviously, we don't get this, we don't directly, note any 0-point energy of this magnitude, okay, right? So it has been postulated, okay, it's been postulated that the field of electromagnetic radiations get cancelled by the field of various quarks, bosons, fermions, etc., of quarks, etc. Now, please don't be upset if you didn't understand this particular sentence. I myself absolutely don't, okay, right? But I just wanted to put it as an information to you that, the 0-point energy's origin is fascinating. We don't know what actually causes the 0-point energy. And if this oscillator model is valid, right, then there should be something, present in the universe of the magnitude of 10 to the power 43 hertz. but obviously it is not noted. So what is currently being proposed and postulated is that, oh, the electromagnetic radiation is not the only radiation that's present. It is cancelled by the field of without even defining a field properly, right? In this course, right? A field of, say, some fundamental particles such as quarks, various bosons and fermions, etc., etc. Okay, right? So the bottom line to the whole ZP discussion in the context of cosmology is that the ZP's fundamental origins are unknown. This particular treatment, of the hydrogen atom molecule, right, using this parabolic potential, it illustrates the idea of ZPE. But the ZPE has significance resonating far beyond your routine astrochemistry, which is, of course, not mundane. Okay, astrochemistry is itself very exciting, but far beyond it, even in the field as esoteric as cosmology, your zero-point energy is extremely critical. Okay, so zero-point energy is a term that you frequently encounter in chemistry. Okay, but it extends beyond chemistry. Is a message I want to give you all. Why is that? That is due to the description of the electromagnetic radiations as nothing but a collection of infinitely many oscillators coupled together. All right. So please be aware of this problem, so that if in case you choose to pursue cosmology in the future, right, you could be aware of this specific problem. Okay. There is so much more. It's a very active area of research, and it has some very big names, ranging from Einstein to very many people, like Hubble, Einstein, Stephen Hawking. So many people are involved in this area of research. Okay, so you can perhaps look more on this in a course dedicated exclusively to cosmology. But the connection between astrochemistry and cosmology is nicely brought out by this idea of zero-point energy. That is all I wanted to convey. Okay, all right. Now let's get back to astrochemistry itself. Now you see, now we started off with the understanding that close enough to the equilibrium bond length, right, of any diatomic system, we can model the potential energy using a parabolic form. The V of x is equal to half kx squared. But it does not apply as we go further beyond, right? Especially in the dissociation limit, right? That is when your potential energy does not change, right, for any distance, right, in the asymptotic limit. We discussed this shape much earlier, right? So clearly it is not a parabola. Beyond certain range, it is not a parabola. So what potential form do we use? Okay, right? The potential form that we use, in these extended regions is something of this form. Okay, right? Beyond just including the parabolic form, to describe the other region, right? The other region of dissociation, right? We use the form something like V of x is equal to some d, where d is a constant, right? Times 1 times e to the power minus x squared, where my x is once again defined as the modulus of r minus re. Now, what is the advantage of using this beautiful exponential form? It accounts for not just the region close to equilibrium, but also takes into account the region which is far closest to the equilibrium bond length, but also the dissociation limit, which is far from the equilibrium bond length, right? Now, as that is the beauty of this function, okay, right? This function, and d is just some constant which has dimensions of energy, because otherwise, right, this whole thing is unitless, right? So your d is some constant having units of energy, right? Okay, so with this, we describe the full potential energy surface, okay, beyond just including a region close enough to the equilibrium bond length with this function. I think this potential is what is called as some kind of it's called as the Morse potential, okay, right? Now, by including this form in the potential energy, we include the most interesting aspect of the potential energy surface, the reduced version of it. But what we still do not take into account is this region, and we don't care much about it, because in chemistry, especially, we are much more concerned with a bond getting elongated and eventually dissociating than like bringing two nuclei together. That is the realm of nuclear physics and chemistry, okay, right? So we don't care about that. So I stopped this lecture by informing you that the form of the potential we use to describe both the equilibrium region as well as the dissociation region is this exponential form, right? Which takes into account the idea that the shape of the curve changes, right, as we move beyond a distance. Okay. So on that note, I end this lecture. A brief summary of what we saw was we started off with a beginning understanding of vibrational spectroscopy, and I told you that by solving the Schrodinger equation, we could get the energy states, and that the boundary condition was tricky to understand physically for the vibrational energy problem, right? And then we obtained what is called as the 0-point energy, which is unlike the rotational part, right? Wherein the lowest energy could be 0. Here, there is a finite magnitude of the lowest energy, and that this 0-point energy is not only critical in astrochemistry, but is also extremely significant in cosmology, which is the area concerned with the origin of the universe, right? And subsequently, I told you finally that take into account the dissociation of molecules also, the parabolic potential energy form needs to be changed to what resembles some exponential one here, right? So with this, I end this lecture, and we'll continue in the next lecture. Thank you so much.